He's a real neat guy. I really have enjoyed talking with him over the past couple days. He has a master's degree in electrical engineering from the California Institute of Technology, a minor degree in artificial intelligence from the University of California, Los Angeles. That's because he believes that artificial intelligence is better than none. He's done and is doing research on gravity and inertial propulsion. He's published several dozen articles on mathematics, gravity, and artificial intelligence. He married Bonnie Kiefer, who has a Bachelor of Science degree in Home Economics Foods from the North Dakota State University. Harvey and Bonnie have 5 sons, 5 daughters, 12 grandsons, and 12 granddaughters. And one of his sons is right there. He's our very able and competent assistant in putting these presentations together technically. And so we know that Harvey and Bonnie did something right there. And then he's worked on the Talos missile system, the inertial guidance system for the Polaris IRBM, the Surveyor spacecraft, the Apollo, the Space Shuttle, Minuteman, and numerous Space Defense Initiative programs. So here's Harvey Fiala.
Drop that in your pocket.
Oh, thank you.
Testing. Is it working? Can you all hear me now? Yeah. Okay. I'm not used to the lights myself. And I might just add, adding on to what he said, John is my son, and his son, John Arthur, is here helping with the videoing. And my wife is here also, Bonnie Fiala. And so there's 3 generations from one family here, and this is the 3rd year in a row that we have 3 generations at either the Tesla or the INE conference. I'd like to mention that I'm not an expert in DC power measurements. I was trained as an electrical engineer, and I wasn't in the power field, but I see such a great need for more entrepreneurs and inventors understanding how to correctly measure power, and so that's why I'm talking on it. And there's probably easily 100 different inventors who've come up with a device where they honestly believe that the power out is more than the power in, and it's that they simply measure the voltage out and the current out. And everyone knows that power is the product of the voltage and the current. Well, that's true, but if they're not in phase, then you have to add a power factor. And if they don't have a very good waveform, then the power factor goes to pot also, and you have to use sampling techniques. And so it's a complicated thing. And after my talk here, we'll have a little demonstration here. Now they say every good speaker should start out with one good joke. So here comes my story. There's a mother and a son. Son name's John, and the mother's putting him through college now. And so he goes off to college, and after a month or so, the mom calls him up and says, "How are things going, John?" He says, "Just fine." He says, "Hey, Mom, I want you to come down and visit me at the college, and we'll have a nice dinner." And so a week or 2 later, the mom comes down, and he's living in an apartment off campus. And so she knocks on the door, and he opens the door and comes in, and the first thing that the mom sees is there's John, and there's a beautiful young lady in the apartment. And John says, "Oh, Mom, I want you to meet Julie here." And so Mom's kind of taken back. She's wondering just what's going on here, you know. And so John, there's a kind of an embarrassing moment there. And John says, hey, Mom, I know what you're thinking, but it's not that. Julie and I were just sharing the apartment here because it saves cost. We're sharing on the cost. We save on the laundry bills. We save on the food bills. And so we're just sharing the expenses. And see, I have my bedroom there and hers her bedroom, so it's not what you're thinking, Mom. So she relaxed a little bit, and she didn't really know what to think, though, but they had a wonderful dinner. And part of their dinner, I'm going to mention, not everyone is familiar with the term ladle, like a gravy ladle. It's a big kind of a spoon where you dip gravy with it, and that's part of the story here. So they had a wonderful dinner, and afterward, Mom went home, and the next morning, Julie said to John, John, I can't seem to find the gravy ladle. I don't know what happened to it. And John says, well, you'll find it, don't worry. So about 2 weeks later, Julie said to John, John, I still can't find the gravy ladle, and I wonder if your mom took it when she was here a couple of weeks ago. And John says, Julie, what would Mom want with the gravy ladle? She's got her own, and, I'm sure she doesn't. And Julie says, well, I've searched and searched, and I just wonder. And John says, well, if it'll make you feel better, I'll write a letter to Mom and ask her. So he wrote a letter, dear Mom, we enjoyed your company and so forth, but we can't seem to find the gravy ladle. And now I'm not saying that you took it, and I'm not saying that you didn't take it, but if you have any idea where it's at, we would really appreciate knowing where it's at. So Mom got the letter, read it, and Mom wrote a letter back and says, Dear John, I enjoyed the evening with you and Julie, and yes, I know exactly where your gravy ladle is. And now I'm not saying that you and Julie are sleeping together, and I'm not saying that you're not sleeping together. But if Julie had slept in her own bed even once, she would have found the gravy ladle. Okay, did that qualify as a good joke? Now, I hope everyone's awake now. Actually, with the blinding light, all I see is a few bodies out there. So, before I get to the subject of how to measure alternating current power accurately, I'll just say a few words about myself. My first love was gravity research. And actually, my first year in college, I went to St. John's University, planning to major in, I wasn't sure at that time, music and mathematics and religion, really. And that was at Collegeville, Minnesota. Then I stayed home 2 years to help my father on the farm, which wasn't very productive, really, farming-wise. And I had to go back to school because there was no future on a farm for someone with some scientific inclinations. And so I went to the North Dakota State College of Science my first year, and I was so interested in gravity research that I had in Einstein's terms, a Gedanken, that's a thought experiment. And after class once, I went up to the physics professor, and I asked him, I have a question. I said, suppose you go way out in outer space where there's nothing for millions of miles, billions of miles, and suppose you put a ping pong ball out there. Now suppose you go 186,000 miles away from that. By the way, that's about how far light travels in 1 second. So here's the ping pong ball, 186,000 miles away. You instantly create a sun or a planet or a massive body. You instantly create it at t=0. Now, then I asked him, how long will it take for the newly created gravitational field from that newly created body to reach out and start pulling on the ping pong ball toward it? And you know what the professor's answer was? He looked at me and he says, "Are you crazy?" Well, that's about how the system treats people who would like to solve problems and make scientific breakthroughs and so forth. Well, that was not a very respectable answer, but it made me all the more eager to. It spurred me on all the more, and in the following years, I had published papers on mathematics while I was in high school, and when I was going to college, I published papers on gravity research. In fact, that's the time when Townsend T. Brown was coming out with his ElectroGravitics, and I saw that. I liked it so much that I corresponded actually with InterAvia. They're the ones that started publishing his articles. And I finally wrote back to InterAvia several times, and they had promised, keep tuned into this in coming issues, and suddenly it stopped. And I didn't know what went wrong. Well, that's the moment that the government classified it top secret. And so there's nothing more. And it was only about 5 or 10 years ago that I realized that, hey, that had been classified top secret, and now it was unclassified, and so that enables people like Tom Vallone and others to get his information and try to replicate his experiments and so forth. And when I went to Caltech, I worked at Hughes Aircraft also for a year or two, for 3.5 years. And besides working on their missile program, I was trying to measure the speed of gravitational interaction. And I corresponded with Dr. Robert Forward and Dr. Feynman, Dr. Richard Feynman from Caltech. He was my instructor and advised me in gravity research issues. And we concluded that at the present time, it is not possible to directly measure the speed of gravitational interaction. So I stopped my project at Hughes Aircraft on that because I didn't want to spend their money on something that I felt that couldn't really be done. And I went back to missile systems technology at that time. But I used to get phone calls from Caltech to go out and check out someone who had an anti-gravity machine. In those days, the term inertial propulsion hardly existed, but I'd go and sometimes I'd take Dr. Robert Forward with me. We'd go and there was nothing to it, it couldn't possibly work. And although I have copies of patents on the devices that we went out and explored, you could still get a patent on it. And there's probably more than 100 patents on reciprocating devices, eccentric devices that claim to work and don't really work. And I can explain them all, why they can't really work and why they appear to work. They appear to work in similar to the guy who measures more power out than the power in. It's they don't know what to look for. And I consider that as the response of a device, the response of a reciprocating device to a nonlinear medium, to a viscous medium. And even if you're moving through air, the air has some viscosity, and even the ether could ultimately be considered a viscous medium. Okay, that's a little bit. When I was at Hughes, I worked with Hal Fox. He's president of the INE, EEMF organizations, and Hal Fox started the Institute for New Energy, and he's a motivating force there. And Hal has said that he's maintained that any anomaly that you come across is really a window into the unknown. If there's an anomaly and you get some of the smarter guys around, they can probably explain it for you. But if they can't explain it in terms of the present physics, then that's something precious. It should be pursued and investigated by very good minds who might be able to figure out, hey, we're tapping into zero-point energy or something, and go ahead and really explore it further. And so every anomaly is potentially a window into the unknown, and should be pursued. Now, I had copies of my paper available here, so anyone who's interested, there should be plenty enough copies. I brought 200 of them with me. Now, in the latter part of my paper, I should mention that Dr. Patrick Bailey is here, and in 2001 at the annual meeting of the Institute for New Energy here in Salt Lake City, he presented a paper on how to measure AC power. It was more theoretical than my talk is right here, but I copied a lot of his words directly. No need to try to reinvent the wheel, but the need is so great for something like this that I integrated his paper. And his paper was also published in the 2004 October issue of the New Energy News, put out by INE. And just in one of the recent issues of Infinite Energy magazine, his paper was also published there. And I maintain everyone here should subscribe to Infinite Energy magazine for sure. Dr. Eugene Maloff was the founder and the editor of it, and he was murdered a little over a year ago. They have a nice memorial issue dedicated to him, or in the last issue. And I obtained permission from Patrick Bailey, who is here. I can't see against the light, but that's okay. And I asked Patrick Bailey, can I have permission to use? And he emailed back to me, and he says, sure, Harvey, give him hell. And he says, you can read them exactly, this letter from the NEN October 2004 issue below, which was published in the Infinite Energy magazine, and you can use whatever you want from my paper. Now, in addition to in Infinite Energy publishing his article, he sent a letter to the editor, and his letter to the editor says, caution, do not use meters, use digital oscilloscopes, by Patrick Bailey. Infinite Energy magazine, volume 10, issue 57, September, October 2004. Letters to the editor. Okay, caution, approaching danger. I read with interest the article in your last issue about the so-called over-unity motors from Japan with rotating magnets. For example, the Techno Maestro's amazing machine, Kohai Minato, and the Japanese Magnetic Fan Company. I fear that the article as printed leads to misconceptions and possibly very wrong conclusions regarding this motor. Editorial note. The article is a reprint of a much circulated internet story. The editor, the late Eugene Maloff, felt that the story was important to share with our readers and hoped it would open dialogue on that subject, which it certainly did. Now we are all working hard to uncover new sources of potential energy and advance physics for a better tomorrow. Yet we need to be very careful. Measurements taken with meters cannot and do not accurately measure the useful power in devices with rapidly changing voltage and currents. Now keep in mind this is still part of Dr. Patrick Bailey's letter to the editor. One must use a high bandwidth digital oscilloscope to measure and store the voltage versus time in digital memory. And then also the current versus time. Then a calculation can be performed to obtain the power versus time, the voltage times the current for each digital point. Finally, the power versus time can be averaged over a defined time interval, which is one cycle, to get the true average power over that time. In this way, the true averages of both the input power and the output power can be obtained, and the efficiency of the device is equal to the true output power divided by the true input power. In all cases, to my knowledge, every single device with rotating magnets and or rapidly changing voltage and current waveforms has proved to be less than 100% efficient. While simple meter readings can show them to be over unity, I can show you a simple RLC circuit that will measure as an over unity device when using meter readings that is actually just a big resistor and is way less than an over unity device. Infinite Energy, he's referring to the magazine, has come a very long way and has built up a great reputation. And readers do not want to see any more unsubstantiated claims by people that do not know how to perform accurate power measurements. Surely the magazine would not publish cold fusion papers with sloppy calorimeter measurements. Allowing such sloppy measurements in published papers only increases the amount of disinformation in print and on the internet and in people's minds, thanks to the editors of Infinite Energy, etc. Actually, I've got good news. Some of you have built over unity devices, and I have also. But the bad news is that the over unity part is reactive energy, also called imaginary energy. And I'll define what reactive or imaginary energy is. How many of you have actually seen an alleged over unity device? That's interesting. At least I can see the hands being raised. How many of you have only heard of an alleged over unity device and not seen one? Actually, everyone should raise their hands on that. And if you didn't, I know that there are like up to 50% of people who never raise their hand for anything. That's just. And how many of you believe an over unity device actually exists today? Wow. That supports the need for papers like this one. Now actually, over unity devices, if you have if you turn the light switch on, suddenly power flows. That could be considered over unity because the device up there is putting out radiant power, but it's coming from a place where we've stored up energy, either in batteries or in the Hoover Dam or someplace, or in big flywheels. And we understand that. But there's, maybe there's at least half a dozen principles, like maybe charge clusters. When they impact something, they may tap into zero-point energy in the vacuum or the ether. Actually, I'll back up a little bit. In the 1880s, Michelson Morley performed an experiment to see if there was an ether. They measured the speed of light in one direction and in another direction, and they rotated this thing around, and they were trying to prove that since the Earth is traveling at a certain velocity in its orbit, if light is going that way, it ought to get there faster. If light is going this way, it should take long. No, if light is going this way, because its source is moving away, it might get there slower. If it's going orthogonally, it shouldn't be affected by the Earth's motion. And in their experiment, they concluded that there was no ether. And of course, that conclusion was wrong. There's been about a half a dozen experiments since that has proved that there is an ether. And I'll start by saying sound waves from my voice to your ears, you get to your ears because there's air here. If there was no air, and me trying to make a sound, nothing would be transmitted from me to you. So sound needs a medium to get to you, namely air. And the question was, does light need a medium to travel? And they concluded erroneously that, light does not need a medium to travel. And And that didn't sit very well with some people. But the establishment, well, okay, so later on it was proved that there is a medium. And so light needs a medium to travel, and so does radio waves. Radio waves are here, they're everywhere. And radio waves and 60 cycle waves. 60 cycle waves have magnetic fields that build up and collapse and build up and collapse. And orthogonal to it, there's an electric field that builds up and collapses. And those electric fields and magnetic fields couldn't exist if there was no ether. Actually, if there was no ether, we couldn't exist either. It's like the substructure of everything, the whole universe. And so, in power measurements, there's three components. There's resistors, there's inductors, and there's capacitors. Now, in a simple resistive circuit, if you measure the voltage across it and the current through it and multiply them, you'll get the correct output power. But if there's any inductance or capacitance in the circuit, there's magnetic energy or electric field energy that goes into the vacuum or into the ether. It builds up and collapses, builds up and collapses. And if you put an antenna there, you'll pick it up. And that proves that there's energy other than just in the conductor and to the resistor. And so okay, you can put the next slide up, John. Okay, now that's a little hard to read, so I have a larger one, so go straight to the next slide, please. No, I have one much bigger than that, John. This is supposed to be just listing all the units of resistance, ohms, inductance, and so forth. It doesn't have a title, but it's a little easier to read. Can you mostly read that or not? Okay, I'll just go over it. Well, yes, but it's a copy that's hard to read, and I've got a copy here. It isn't necessary that. There's a lot of copies up there. I'll start right here. There's a symbol for a battery, hand drawn, and that's really a source for DC current. Then over here is a symbol for an alternating current source, which is what we're concerned with today. And the next symbol is a resistor. Its units are ohms, and it dissipates power. It heats up if a current flows through it. The next symbol is an inductor, and the units for inductance is the Henry. The symbol is L, standing for inductance, and the symbol for the voltage drop across it, or rather the impedance that it presents, is given by X, in this case X sub L. And then here's the symbol for a capacitor, and its symbol, its units are farads, and its symbol is C, and its reactance is given by X sub C. There's X sub L and X sub C. And this is an Excel spreadsheet. Normally, X sub L is equal to I omega L. And I couldn't get the Greek symbols, so I wrote the word out, omega. And the capacitive reactance is 1 over omega C. And the next one is electric potential. and that's in volts, and the symbol is typically V for volts or E for electric potential. And an equation for it is IR, the, current times resistance through it. Then we come to current. Let's see, actually it's hard for me to read it. Also, it's kind of fuzzy. Now that is different. Okay, I have a different sheet here, which from up there, you don't have a way to display this sheet without a transparency, do you?
Okay, no, you know what, I don't have that
Okay.
transparency with me.
Anyhow,
If you like, may I? Can you speak to it directly on the?
well,
You'll have to read it off the,
yeah, I have a copy here. Okay, current is in amps. The symbol is I, usually, or A for amps. And an equation for it is voltage over resistance. And the next, an imaginary, now here, a lot of the entrepreneurs or inventors, they're not electrical engineers. And this is so basic that I'm going to skip down to impedance. Let's see. Okay, there's impedance. And it's actually, Z is the symbol for impedance. It's equal to the resistive component plus the reactive component. There, that's great, John. Very good, thank you. The resistive component, and now electrical engineers in Electrical Engineering 101, they learn what that symbol means. It's either an I or a J, and it's actually equal to the square root of -1. And if you talk to an entrepreneur or an inventor who hasn't been trained, I mean, some of them talk about current, when they mean current, they say juice. And they don't really even know what the units of volts and amps and resistance and so forth are. And so that's, X is for reactance. An inductive reactance is positive. Typically when you show resistance, you show it along the x-axis. And if there's reactance in the circuit, you show it along a vertical axis. If it's inductive, you show it up. If it's capacitive, you show it down. And the total impedance it's the hypotenuse of it. Well, I won't dwell too much on these. Okay. And the magnitude of the impedance is actually equal to the square root of the sum of the squares of the two components. The resistance squared plus the orthogonal component squared. Then you take the square root of that, and that gives you the total impedance, which impedes the flow of current. And work is in joules. 1 joule is 1 watt-second. And then energy is also in joules. They have the same units. And power is in watts. It's equal to I squared R if the circuit is only, well, resistive. Pure inductance and pure capacitance does not dissipate any energy, although we know that there's some resistance in any capacitor and in any inductor because they conduct electricity. Power factor, typically designated by PF or power factor, and it's equal to the cosine of theta. And again, I couldn't get the Greek symbol, but theta is the cosine. If you have resistance here and reactance here, the hypotenuse is like this, and there's an angle between them, and that's the angle theta. And so the power factor is equal to the cosine of that angle. Now, magnetic flux is measured in Webers, and that's symbol is M, and B, it's a total amount of magnetic flux. We'll go back. And the flux density is in Gauss. It's Webers per square meter. And the magnetic permeability, mu, is really a ratio of how much magnetic flux you can get in a material like iron compared to how much you can get in a perfect vacuum. And electric charge is in coulombs, the field intensity in volts per meter, and its units are force divided by the electric charge. And permittivity, again, is how much electric field can you develop in a substance compared to that which you could create in a perfect vacuum. And by the way, you see a name there. Dr. Derek Gerlach, I was speaking to him last night. He wrote a paper. He's not presenting here, but it's a very interesting paper. A man named Dr. Harold Aspton, who lives around London, he's ready to jump on any potentially over unity device, and he looks at it, and if it looks like it could be, he jumps on it and puts out an article with his theory of how it happens, and which is a very, very healthy thing to do, and it invites others to. But Dr. Aspton, I've corresponded with him. He came up with a magnetic circuit. If there's an air gap in it, after you turn your primary current off, he said that there's still enough magnetic energy stored in that air gap, which is actually more than you put into it to start with. And if that were really true, that would lead to an over unity type motor, and also called perpetual motion. And if you really are able to build something like that, and it's tapping into zero-point energy or some other source, hey, that's great. And I'm not saying it can't be done. You got to keep an open mind toward it. But Dr. Derek Gerlach, he wrote a paper. He gave me a copy last night. I read it, and it's excellent. And he very, very carefully replicated that and showed that he couldn't detect any residual magnetic energy stored in the air gap of this circuit. And so now he's had time to reflect on it and study, but Dr. Aspton, he looks at something and jumps right on it. He's written a few books on gravitation. I have most of his works, so I'm very familiar with him. But his first article usually there's a flaw in it. But he's a good man. We need 1,000 more like him. And okay, I guess that's enough for the units there. You can go to the next slide now, John. Now, okay, here's a typical, that's a alternating current source, alternating voltage. And here's a typical, the symbol for an inductor, which is reactance. And here's a resistor, and you measure voltage out like that. Now, these are two discrete components, but we're going to let it represent a device, maybe a combination of magnetic circuits, motors, and resistors or capacitors or transformers or whatever. And these inventors, they go measure the output voltage, and you can measure the current by measuring the voltage across the resistor from here to here and dividing by the resistance. That'll give you the current. If R is equal to 50 ohms, and I have a 50 ohm rheostat here which we're going to run a test on, 50 ohm rheostat. And so there's 50 ohms of resistance, and we've set it up so that there's about 50 ohms of reactance also. And that inductor, well, okay, now if you have a diagram here, you show resistance along the x-axis and the reactance along this axis, and since it is inductive, I showed that as positive, and that convention is what's used in the Handbook of Radio Engineers. And if you take this arc and swing it over here, because if you measure with the voltmeter and an ammeter and take the product, you'll get this much power, but only this much is the real power, and this much here is extra power. It's actually called imaginary power or reactive power. Actually, I showed that just as the difference, but the total reactive power is here. And since I set this up for 45-degree angle, because that's easy, that means the resistance here is equal to the reactance, and so that's 45 degrees, and the square root of 2 here, if this is 1 and that's 1, that's square root of 2, so that's exactly 41.4% over unity if there was a source that had no losses in it. And so that kind of tells you the average person, the average guy who thinks he has an over unity device, he's measuring this much, whereas it's really only this much, and he has to forget about that. He can't use it. It goes into and out of the ether 60 times a second, actually 120 times a second. It swings up, positive, and down for the negative part of the cycle. So that energy goes in and out of the ether 120 times a second, both magnetically and electrically. And so here, this just tells what I've just told you so far. So now let's go to the next slide, John. Now here is a way, if you don't have anything fancier than an oscilloscope and a voltmeter, that's all you need to get pretty good measurements here. Here's power. Here's an isolation transformer, so you don't kill yourself. The output is floating now once it's isolated here. And this shows an inductor and a resistor. And if you measure the voltage across the resistive part only, which in a device you probably can't separate it, so you need a current meter, or you need a clamp on ammeter, which you just clamp over. So this waveform here will be proportional to the current, and the voltage that you measure up here will be proportional to the voltage. And as you can see, since there's an inductive reactance here, which I purposely set equal to this so that there's 45 degrees. Now in this waveform, there's a 45-degree difference. One is lagging the other by 45 degrees. And so the cosine of 45 degrees is 0.707. And that's equal to the square root of 2 divided by 2. And so now raise that slide up, so we'll go to the bottom half of it. Okay, now here is identically circuit, except we have a capacitor up there. And again, I would set the capacitive reactance equal to this just for ease. And here the phases, here the voltage lags the current instead. And this tells all about A and B. And so if you have an oscilloscope and nothing better, you would try to actually from this point here over to this point, that's 180 degrees, that's 360 degrees. From here to here, that's 90 degrees. And if you divide that into 4 parts, This would be 90 degrees. Here's another 90. And you can see that's about halfway. So that's about 45 degrees. So you'd have to estimate it. But even if you estimate it, and actually you wouldn't go to here to try to measure that voltage. You'd put a voltmeter, a digital voltmeter across it. And you'd put a digital voltmeter across here and here. And you get those readings. They're RMS readings, root mean square. And you would take the angle that you approximate here, take the cosine of it, and you would have a number that's within a couple percent. And that'll be much, much better than just taking volts times amps. And so now we have a setup here with a capacitor. This is a capacitor here. Actually, it's about a 50 microfarad capacitor. No, wait a second. That's well, it's chosen so that it'll give about 50 ohms of reactance. And this can vary, this rheostat can vary from 50 ohms down to 0. Of course, you don't want to go way down to 0, then that's like a short circuit. And so, and my point here is that you can find AC capacitors much more readily than inductors. An inductor is like a transformer or a Tesla coil or a motor. Most electric motors appear inductive, but so we have, we chose a capacitor. Now this part here is supposed to represent a device. Here, the reactance and the resistance are truly separated. That's going to make our test easy. But in another device, you can't separate them that easily, but we'll be able to demonstrate the principle involved. And now let's go to the next slide. This shows, now this is from the part that Dr. Patrick Bailey presented and was published in New Energy News and Infinite Energy. And here, that shows there are 5 degrees. There's only a 5-degree difference there. And the cosine of 0 degrees is 1. The cosine of 5 degrees is almost 1, like point. Actually, it's, and you have to take half of it. But if you double that, you get the cosine. The full power would be 0.5, and you see that's 0.498. Let's go to the next. Okay, here's the voltage and current waveforms with a small 5-degree difference. And if you multiply them, you get the power. And you can see that it's almost full power. And so, next slide, John. Now here we're up to 15 degrees. And so you can see there's a little bigger angle there, and the power is dropping a little bit. It's down to 0.43 instead of 0.5. Next slide. Now, let's see, this is figure 5. Okay, that reads 30 degrees, a little hard to see. And you can see that there's about 30 degrees, and the power falls off. It's down to 0.43. Okay, next slide. And here, thank you. This is 60 degrees, and we're down to 0.25. And now you can see that, like from here, okay, you can see that's about 60 degrees. And now the peak power is down. Here's the peak of a current cycle, and here's the peak of a voltage cycle. And here, you'll get this peak, I believe, right at that point there. And it's down. Now, if this is 60 degrees, And we've set my experiment up for 45 degrees. And so, okay, let's go to the next slide. Okay, this slide shows the average power. Now, as you go out to 90 degrees, the cosine of 0 degrees is 1. So you're going to read essentially full power. And the cosine of 90 degrees is 0. So your actual power drops to 0 if they're totally out of phase. That's like as if there's no resistance at all in the circuit, and it's all inductive or capacitive or a combination of the two. And this line here represents the power that you think you're getting if you multiply voltage times amplitude. And so you'd think you're getting, you're really getting 0 voltage, 0 power out, but you think you're getting like 30% of the full voltage times amperage. Next slide. And here, again, if it's only resistance, the phase angle is 0, the cosine is 1, and this is your fictitious power gain. Well, you're reading the real power, so it's unity. What you read is what you really get. And of course, if you go out to 90 degrees, this goes up to infinity. It makes it look like you're getting infinite energy out of it. And we, in this experiment, we're operating at 45 degrees. And we see here that this is plotted for 10% over unity. And we see, if we're operating here 45 degrees, I'm going to go straight up. And this is the 50% power. This would be a 50% over unity. And we see that if we take 45 straight up, we're at 41% as we shown the cosine of 45 degrees is 0.707, and that leads to an over unity of 41%, if you could believe it. But so that explains that slide. Now let's go to the next one. Flip it over, please. No, that's right. No, that's right. Okay, this is a actual current waveform in a motor that's running unloaded. It's the idling current. And you can see that it's not a very beautiful sine wave. This is like real life now. And there's inductance in the circuit and some capacitance. But a true sine wave based on here, it'll like start here and go up and down like that. So that just gives you an idea what real life is like. And I'll mention at this point that Harold Putoff submitted a paper entitled The 1 Watt Challenge, and to be given to any over unity device researcher, which basically says, close the loop and show me how you can produce 1 extra watt of power or shut up. This open challenge still stands for all rotating magnetic and AC frequency devices. And and furthermore, that paragraph was taken from Dr. Bailey's part of this paper. And he follows that with saying the INE, Institute for New Energy, will be more than happy to recommend to any researcher the name and address of an independent test engineer who would love to analyze your favorite free energy machine in this manner. Almost all the so-called over unity devices and free energy machines that you will find advertised in the US and even internationally will be false because of the facts explained here in this paper. The I&E will continue to track all of the devices and machines that it is aware of and show any shortcomings of each. The I&E will continue to contact all researchers that claim to have such electricity generating machines and to offer our known research engineers to test and calibrate their device or machines. All results and ignored requests will be documented and posted on our I&E device database website. The I&E is continuing to look for new devices and machines that will really work as new forms of potential energy are continually being discovered and understood. Now the I&E, Dr. Bailey has a website, and it lists like over 100 different devices. And if I came up with a device that I thought might be over Unity or something, I should write it up, describe it, and submit it, and it'll be listed there, and all of you can log on and see a list of all the devices and any critiques or comments on them and so forth. There's none that have been tested. By golly, it works. You know, they all have shortcomings, and sometimes there's a device listed there that no one has taken the time to test, and I'm sure there are minds here which could look at those and find the problems with them, and so you're encouraged to go to that website and study those devices. And the important thing is, for every one of those devices, there should be someone who's authentic enough to say it can't work and here's why. Then people would stop wasting time with that or stop investing money in it. Like there's a lot of devices out there on the internet that are trying to get investors, and some of them are fraudulent, and some of them actually believe that if they had $1 million or more, they could actually finish the development of it and make it work. And but so if someone could prove that it can't work, then we could save our energies for what is real.
Dr. Kudoff is actually skeptical of the Newman machine. He says I talked to him about that one time.
Pardon?
The Newman effect.
Yes.
Hold on a second, let me.
So any comment?
On the Newman effect?
Yeah.
Okay, I'm actually not that familiar with it myself, so you're probably you have more information on it. What is your information on the Newman effect?
Well, it involves a short circuit at a continuous changing of impedance, and it's supposed to put out more energy. What it puts in, and he's using his Newman device for electricity in his own home, you know, right now, but to give excess current. But that's what I understand about it. Just off the top of my head, I'd have to look up information to get more detail.
Okay, basically, I'm not that familiar with all the devices myself, but I rely on people, actually like Dr. Aspen or Hal Puthoff or Dr. Bailey or published articles that draw a conclusion about that, and I'll accept that rather than become, you know, totally familiar with the device myself. Yes.
The Newman machine is being tested or was tested by some government agency, and then Newman claims that they didn't test it the way that it should be tested. So the way to handle all of this is to have these machines tested using the proper instrumentation, doing it the way that the inventor says to do it, and find out for true. There's just too many tunable knobs, and we have to do it the right way.
Okay. Thank you. Let's go to the next pack of slides. Now, just 2 days. See, I retired from electrical engineering or computer engineering in 92, just for health reasons and chronic fatigue and things like that, and so I haven't kept up with the instrumentation, but just 2 days ago I says, hey, I should come up to speed on it, and I looked on the internet and I found there's a EAMS company on the East Coast, and they have a power meter at 3910, and notice that That measures amperage, voltage, kilowatts, true kilowatts, and there's the cosine of the angle, which is 1. And this meter costs $695. It's a very good meter, and someone at the Tesla Foundation or INE or some of you guys who had the money, that'd be a good investment to get, because you could walk up and test. You could test.
A meter just like that here, but it's at the hotel.
Pardon?
I've got a 2-meter like that, K-bar meter.
Okay, very good, excellent.
I would like to look at it later, I'll bring it.
And your name is?
Forrest Pittman.
Okay.
Matter of fact, correct.
Now, the next slide, this, it's just another picture. Let's go to the next one, please. Okay, this talks about the construction of it. It's not much different, but it defines basically the controls on it. So we can go to the next slide now. And now here, this device costs anywhere from $3,200 up to $4,000. And it's supposed to do everything the earlier one does, but it does so many more things. It shows all the waveforms, and it calculates up to the 50th harmonic and everything. And it's a Cadillac of a thing where maybe you only need a bicycle or a Chevrolet. But this is a Cadillac of it. I just showing you that there are devices out there now. And let's go to the next slide. That's a model 3945. And since it's not easy to read, let's just go to the next slide. This shows the type of waveforms that it, this is harmonic content. The harmonic content drops off after you get to higher harmonics. And this, you're supposed to be just impressed by what this power meter will do here. That's the only reason for this slide. Next one, please. And here's more waveforms. It shows the power waveform, the current waveform, and maybe the voltage waveform, but it's just impressive what it will do. Next slide. And here's the specs on that box, on that meter. Now I'm not trying to advertise for this company or anything, but they do build a very good product. And one reason I'm showing this is because they've lent us a meter here, the 3945, and it's here. And so, by the way, is Jim McIntyre here by any chance? He's the rep, and he loaned this to us for the duration, and he said he might come and see the presentation using his meter. Okay, here's just another. This is all the stuff it can do for you. So let's just go on to the next one, John.
This is the software that goes with it. It's just a demonstration of the PC screens that you see, because you can do an active download and full analysis with their software.
Yeah, there's software associated with it. It's a computer. And the reason I'm showing this is because Dr. Bailey's article talks about, a very fundamental way to do it, sampling with the high rate oscilloscope, measuring the voltage and the current, multiplying together, and doing that many times during one cycle, and getting the average of those powers, and that's the true average power for that, like within 0.01% or something like that. This device here measures it 256 times during each cycle. That's every 62.5 microseconds, which is pretty respectable. Now, now I'm going to, so we set up here, and I'm going to mention that even though this is supposed to I can measure the volts and the amps on it, and it's so complex that I couldn't figure out how to measure the power on it. There's so many controls on it, so we're going to measure the power by multiplying voltage and current, and we know the phase angle. So, but I haven't had enough familiarity with that machine. This is the current probes that come with it. And let's show the last one. Okay, there's like the price, $3,200. When we were back with the 3910, there was a price of $695. And I'm realizing as I'm coming up to speed that the model 3910 for $695 is plenty good enough to go test a potentially over unity device. This is a Cadillac that does far more than you really need. So there's the $695 price on the, and I think that concludes that part, and we're going to, if you could turn the lights back on now, we will begin with the demonstration. Now, you can help me, John, and you have that current probe.
Okay,
Oh,
the high voltage?
yeah, I'm gonna turn this off yet until you borrowed the current probe for the other experiment, remember?
Oh, excuse me.
Here's this device, and I'm going to liken it to, you know, most of you have a PC, and most people on Earth, it's like our brain. They say we use only 10% or less of our brain. A PC has so much capability built into it that most people use 1% of it. You know, they'll write letters or send emails. That's what most people do. But of course, we here, we use full 10% maybe. But it's got so much capability that.
Okay, you're all set up, 1, 2, and 3.
And this is just like that. It'll take me a little while to learn to use that thing, and I haven't had the chance to do that. Now, from where you're at, you probably won't be able to see the waveform on here, but okay. Now, is this the? Yeah.
Restart it.
Okay.
Okay.
I'm going to place these in proximity here. Okay, what we have here is an isolation transformer so we won't get shocked. I'm stepping it down from 110 volts down to a lower voltage. And the secondary on the transformer feeds into a capacitor, and the output of the capacitor goes over to this rheostat, and the bottom end of the rheostat goes to ground, which is one side of the secondary of the transformer. And this is a heavy-duty rheostat. I turn it like this, and there can be 50 volts on it, so it should not be too harmful. And I'm going to take a couple of readings, and although we're not set up so that you'll be able to see the values, but I'm going to turn this on now, and this resistor starts heating up. And here we see that we have 46 volts across the resistor. And the current reads 1.04 amps. And the total input voltage is 119.7 volts. Okay, I'm coming 1 to 1. 119.7 volts. And now I'm going to change the load on this. And let's see, the current is roughly 1 amp. I'm going to change this down to where the current will be approximately 2 amps.
John, put this as the feed. Pardon? Put this as your feed. Can you feed this to the family, to the projector? Send this signal.
Now it reads 1.96 amps, and the voltage is 119.9, and the waveform is more triangular. You can see that even with a simple device like this, we no longer have sine waves, and that reads 8.8 volts across the resistor. 8.8. And now I'm going to turn it off. Can anyone? Uh-oh. I don't know what. I must have bumped something.
Just the little,
Oh, okay.
little device that's
Okay. Let's see. Can anyone see the waveforms on here from where you're at?
okay.
Probably not. But they're there.
Here, I got it.
And I turned the power off. Now, the point is that this capacitor and this resistor represent a device which is supposed to be over unity. But in this, I can actually separate out the resistive component. That tells me what the current will be. And I know the voltage across it, so that tells me what the current is. But normally you can't get inside and measure the voltage drop across the resistive part of an over unity device. And so all they do is measure the output voltage, which in one case was 119, we'll call it 120, and the current was 1.04 amps, we'll call that 1 amp. And so the current times the voltage will give you 120 volt amps approximately, and the voltage across the resistor was 46 volts. And since this looks like from 46 up to 120, now these are, just a moment, the power, yeah. 1 amp times 46 volts is 46 volt amps. This looks like 120 watts out compared to 46 watts in. And so that looks highly over unity. Now we'll go to the other condition. I changed the current to read 1.96. We'll call that 2 amps. And the 119.9, we'll call that 120. And that gives you 240 watts. And the voltage across the unit is 8.8. We'll call that 9. And the amperage was roughly 2 amps. So 2 times 9 is 18. So here is just 2 different settings. This could correspond to being under load. And it goes from 18 to 240. Under load, it looks like it's 20 would go into their 12 times. This looks like there's 12 times as much power coming out as is going in. Here, it looks like there's maybe 2.5 times as much power coming out as going in. And so this demonstrates the fallacy in just taking an ordinary voltmeter and an ordinary ammeter and measuring the output power and input power of a device. In this, because I measure the input power of the resistor alone, it assumes that the source has no losses itself. Actually, if you have any device, let's say you put 100 watts in, you're going to get less than 100 watts out. If you were super lucky, you'd get 99 watts out. But in general, you'll get 70 to 80 to 90 watts out, depending on the efficiency of the device. And then if it did some magic or tapped into the 0-point energy, then you might get 120 or 200 out. But normally if you put 100 in, you're going to get less than 100 out unless you tap into some form of energy. And I'm not saying that you can't. And it's important that, first off, it's important that the experimenter understand how to correctly measure it. And if he can't understand it, then, like Dr. Bailey says, don't waste your time any longer on that. But if people need to keep trying, because someday someone, the 0-point energy is out there filling the ether, and it's there. And we just have glimpses into it with sonoluminescence and charge clusters and plasma phenomena and maybe even precessing gyros. There's at least half a dozen valid things which could tap into. Now, I'm just going to say that whatever they call it, vacuum energy or 0-point energy, and it's in the ether because light needs an ether to travel. Electromagnetic waves and radio waves need an ether to travel. And if it wasn't for an ether, even we couldn't be here. As we've seen from a lot of the displays, every cell in our body has got perpetual motion in it. There's electrons and stuff keeps running. So if there was no ether, we wouldn't be here. God created the ether. It's like the foundation of everything. Human beings, inanimate objects, radio waves, light waves, everything. And so this concludes my demonstration. Are there any questions? Okay.
We can do questions up in the lobby.
Okay.
Yeah, now, why is it that you can't take a current amplifier circuit and a voltage amplifier circuit and then have them both come out as an output that gives over unity?
I tell you, let me talk to you in the lobby on that. So, thank you, everyone.